Yeah, so sign up sheet for advising appointments. Does anybody need that? Those of you, we had some problems scheduling Agro 310, the soils class with the second semester of barn duty. For the short run, the solution for that is to just sign up for the 110 class, and then we'll do an override for the 151 later. So get your 110, get your lab in for that, and then we'll take care of the 151 later. Don't forget, we've got uh, the student success seminars, this one tomorrow, defeating test anxiety, has proven to be very helpful to a number of students. So we've got forms for that. If you want those up there, remember we're asking you to do one of them for the semester. So review sessions, for anybody who wants to, will be down the hall in 125B, or I'll try to remember teams at 2. We'll be in here at 5. If anybody wants to go over stuff, there's an advanced nutrition class for the spring. If you want to sign up for that, 100 is the required class for it. Thursday, we'll be doing lactating rations. We'll be adding a layer of complexity to define the animal side. Dairy Club meeting tomorrow, 1 o'clock here. For those of you interested in going on the trip, they're going to California in January. There's supposed to be a discussion of that, basically an outline of the trip, what it's going to cost, and those interested. Exam 2 is here on Wednesday. Does everybody feel comfortable being tested on the ABC D fractions of protein? This means yes, this means no. Got some no's. So you want me to back this up to 18? 11 through 18? Okay, I'll get the coverage posted this afternoon. You've got the related topics in lab that don't include feed ID. That's a separate test. Hay quality, that'll be on the lab practical. Sampling and ration balancing will be on the lab practical at the end. So exam's going to cover lectures 11 through 18. Commissioner Ball, Ag and Markets is going to be here on Friday. Anybody who wants to attend that up to dairy, that's from 12:15, 12:45. He's a fun guy to talk to. We'll also be having an open house this Saturday, and there'll be an opportunity for extra credit there if you want to come and promote the program. If you think there's some benefit to being part of Morrisville, the ag business, the ag science, dairy programs, those are the ones I'm involved with. But if you want to get involved with the equine, we can do that as well from my class. So having students there to talk to students is very important. So if you can be a participant in that, usually we meet over in the rec center, like 8 to 11. And then there's a meeting somewhere, usually at 11. And then we usually have tours up at the dairy. I'll define those as we go forward. Jake Wells not here. Anybody want to help him? Okay, so last time we broke up our protein fractions. We'll save this for the final exam. So you have some weeks to get that under your belt. But learning it right now, what happens, taking your letters out to Dr. Mooney's A fraction in crude protein in the rumen. What is the best answer up there? A, nothing. B, converted from protein into amino acids. C becomes part of the microbe's protein. D takes a right at the reticulum and a left at the cranial pillar. What do we know about the A fraction? What is it? As for the most part. What's in it? NPN, non-protein nitrogen. So the best answer for this is C. If it's going to be any of these answers, that's the one most likely. The nitrogen, non-protein nitrogen, will be taken by the microbes and turned into protein. If we're saying it's non-protein nitrogen, we can't do the protein into amino acids. So we're looking at the A fraction available to the microbes, available to the cow, mostly soluble intake protein. What happens to the D fraction of crude protein in the rumen? Same choices. Probably the most descriptive one is A, nothing, but you could probably say D is also a viable answer in that case. So it's inert, it's not available to the cow, it's not available to the microbes, nothing happens to it in the rumen. So we're looking at that D fraction, bound or unavailable nitrogen. That is part of that rumen inert, rumen undegradable, and that C fraction that most of the standard nutrition programs talk about. What about the B fraction? What happens to that in the rumen? By definition, C, B, or C. So it's true protein that is going to be broken down into amino acids that the microbes will use. It becomes part of the microbial protein. Last fraction, C. What happens to that in the rumen? Best answer is probably A, but D also works. So by definition, the C and D fractions, nothing happens to them. What's the difference between the C and D fraction? The cows have access to it. They can digest it in the small intestines. So nothing happens to the C and D fractions in the rumen. We get to the small intestine. There's an opportunity for the animal to digest and absorb that protein into amino acids. Those amino acids are then absorbed. How are we doing in the understanding of this? So which is an essential amino acid? I'm going to ask you to be able to recognize the essential amino acids. If somebody's coming to you selling stuff and it isn't an essential amino acid, there better be a damn good explanation as to why they're selling to you. So which one is the essential? Lysine, essential. Threonine. So what are the two sources that provide the cow with all of her amino acids? What is the sources of amino acids that the cow has to live on? Anybody got any thoughts? So whatever shows up in the small intestines, the cow takes that protein, rips it apart, makes the amino acids. Those amino acids are absorbed. Those are what the cow has to work with, at least to get started. It can create some of its own in the liver. So if we're thinking about ruminal fermentation, what is leaving? We've got things going in. You got fermentation in the rumen under the control of the microbes modified by the cow. We've got microbial protein and undigested feed leaving the rumen. These are your two sources of amino acids. So you've got the microbes that become part of the cow's amino acid supply, and we said that's going to change the profile from not one that's not as good, the plant protein, up to the microbial protein. That microbial protein is more suited or more matched to what an animal needs. So out in the real world, that has an opportunity to help that animal do better. And then we have the C fraction, that undigested feed, the proteins that she has access to, the nitrogen she has access to, can be digested and absorbed, and the cow can live on those two sources. So the microbial protein, which was what? The A and B fractions. And then we have the C fraction, or the undigested feed in the rumen, the unfermented feed in the rumen. There. So we need for our cows, what she needs is amino acids to the small intestine. Where do we get those from? The two sources are microbial protein and the feed protein. So the microbial protein was that A and B fraction. The microbes get a hold of that, the non-protein nitrogen and the true protein nitrogen. They are going to rearrange, they're going to modify, they're going to switch things around. They're going to use it for their own ends. They're going to turn it into microbial protein. That microbial protein then becomes a source of amino acids in the small intestine for the cow. The feed protein is the C fraction by definition, not modified in the rumen, but available to the cow once it gets to the small intestines. So if we're looking at the amounts related to what comes from where, the A and B fraction might account for half of the protein that a cow or a heifer uses, dry cow uses in her small intestine. So we think more of a half is probably our lactating cows. 3/4 is going to be our dry cows and our heifers. That is going to be their amino acid source going through. So they're going to be non-essential amino acids in that thing there. That makes the load of the liver trying to make new ones a little easier. We've got the essential, and this is the only place we can get them. The mix of microbial protein and feed protein at the small intestines has to be balanced for our essential amino acids. These are how the small intestines is where things are decided as to which is the limiting amino acid. Usually it's lysine, usually it's methionine going through. So we're thinking about lysine and methionine and advanced ration balancing and more sophisticated feeding programs. You're going to consider balancing for lysine and methionine. If you're doing all things right and you're making sure your dry matters are dry matters are up to date, everything is good there, you're good at mixing, you're good at putting together a ration accurately, you're making sure that our rations are up to date, our sampling's up to date. If you've got your feeding level, the rations you're putting together for that program at a high level, then it makes sense to consider lysine and methionine ratios predicted to the small intestine. If you're not putting really effort into your feeding program. If it's not a precision feeding program, there's no real need or no real benefit to start adding limited amino acids, protected amino acids to the diet, because your limiting area in nutrition is somewhere else. But if we're good at putting together our rations, we're accurate in our ration balancing, we're up to date on our sampling, keeping our dry matters up to date, there should be some benefit to adding those protected amino acids. So we put protected amino acids into the diet. Protected amino acids would fall into which fraction, A, B, C, or D? They are by definition the C fraction. They go into the rumen. They are unavailable to the microbes, but they should flow to the small intestines and be available to the cow. So they cost a little extra for them. So if I've got everything figured, if I've got everything estimated reasonably accurate, then there's benefit to that lysine and methionine coming in. If I can't even guarantee how much forage I'm getting into a cow, there may not be an opportunity or benefit to doing the protected amino acids. So if we get the most limiting nutrient to the small intestines, the cow should make more milk or milk components. So if there's something limiting milk, whatever it might be, we have to have a situation where lysine and methionine are the most limiting, and that's usually after we've done a number of other things to make sure that energy isn't limiting, make sure NDF isn't limiting, all the things that might be holding those cows back. We need to take care of those first before we need to worry about dealing with limited amino acids for milk production. So how do we get more of the limiting amino acids to the small intestine? There are a couple different ways we can do that. We could feed more, potentially. So if our limiting amino acid is methionine, if I can throw some fish meal in there, if I should throw in some corn gluten meal in there, those are high in methionine. Fish meal is not the most tasty stuff to a cow. So there may be some limits as to how much you can include. Depends on how well you can disguise that fish oil. That fish oil also can lead to milk fat depression if we're not careful. We need to balance things. We need to make sure we're not overdoing it with the fat. If we're limited in lysine, we've got blood meal is a good source of that. Again, fish meal is a good source. And then our processed soybeans or roasted soybeans can be a good source of that lysine. Problem is, we start to put those in, we're going to make the ration more expensive. We can consider the cost differential between just more protein in the diet or ruminally protected amino acids, keeping them in the C fraction. They go into the rumen, they move through, and they are freed in the small intestine after the acid wash, after the base wash there. Another way we can get more methionine and lysine is to produce more microbial protein. Can we get the rumen doing more of the work? Can we get better growth rates in our rumen for microbes? So if we're looking at this as a C fraction, which one is this? A and B. So if we can go through and establish a ration that promotes growth of those microbes, so putting a little yeast in sometimes adds a vitamin mineral mix for the microbes in the rumen, making sure that we balance things out, making sure we add a little bicarb in there, making sure we keep that rumen balanced keep the digestion, the fermentation of that NDF at maximum. That maximum fermentation should lead to more microbial growth. More microbial growth should lead to more amino acids getting into the lower tract, and our microbial protein tends to be more balanced in lysine and methionine than our individual plant proteins. So our goal ultimately is to figure out which is the most limiting amino acid and get more of that amino acid to the small intestine. The challenge is figuring out which one that may be. As we said, with the chickens and pigs, or even our equine, what goes in the mouth is equal to what gets to the small intestine. With our ruminants, that is not the same. What goes to our animal there may be very different than what ends up in the small intestines because of the changes of the microbes in the rumen. They're going to change a lot of things around. They're going to do some things that we may not be able to track. We can guesstimate what they are. We can guess fermentation rate. We can guess passage rate. We can guess degradation rates. So, but again, they're guesses. Sometimes we get them right and sometimes we don't. So our job, at least in our more advanced ration balancing programs, is we're looking at a 3-to-1 ratio of lysine and methionine at the small intestines. That seems to be the best for promoting milk production and component production, particularly milk protein. That seems to be the best there. So we have a series of equations that predict how much will be fermented, how much microbial protein will be produced in the rumen, how much will pass to the lower tract, and then between the C fraction and the microbial protein fraction, we add everything up and we say, hey, is our lysine and methionine in a 3-to-1 ratio at the small intestine? And again, we're looking for something that needs to be best guess, and we're looking at ration balancing program or feeding programs that are at a high level before we start worrying about things like that. So that's a reference for that discussion. So our two sources for our cows is the microbial protein, which can be 1/2 to 3/4 of the protein that they live on, and the C fraction that goes to the small intestine. That's what the cow has to live on, and we focus particularly in those two fractions of what essential amino acids are there. Those are our only source, our only way to get those. The non-essentials we can play with at the liver. So looking at the crude protein requirements, we're looking at pounds of protein and then what those percentages usually end up in for our cows. So we're looking at less than a pound of crude protein for a 200-pound calf. So 0.8 to 0.9 pounds of crude protein per day, depending on the volume of feed going in. That might be anywhere from 14% of the diet to up to 20%. We look at those weaned calves or about to be weaned calves. They're going to have a similar protein concentration to the lactating cows when we get to those. 700-pound heifer, we're going to double that protein requirement. So she's more than double that from a body weight standpoint. So we're getting the percentage of protein per pound of body weight is going down. So what she can eat a whole lot more. So we're looking at 10 to 12% protein, which is pretty easy to achieve most days. Dry cow, we're looking at that late pregnancy range, 2 to 3 pounds of crude protein a day, especially as that fetus is growing at hyperplasia. The blueprint's all laid out. It's just growing that pattern out, dividing cells, more and more cells in there. Again, 10 to 12% of the diet usually gets it done. A lactating cow producing 100 pounds of milk, we're looking at 10 pounds of crude protein a day, somewhere in that range. And we're looking at 16 to 18% of the diet as crude protein. So if you're looking at 100 pounds, pretty standard these days, 3.2% protein. A third of those pounds are going out in the milk. And then to keep that machinery going, keep her body going, we're going to need another 6 pounds of crude protein to get that done. So if we can predict, as the prediction of amino acid supply in the small intestine gets more precise, the lower the crude protein is needed. So in my lifetime, we've gone from almost all lactating high cow rations were about 18%. We're stepping down into that 16 and a half, some places 16, if they've got enough dry matter intake and a good fermentation going. Most of them are 16 and a half, 17. So we've dropped down 1 percentage point because we're not wasting. We're doing a better job of partitioning. We're getting a better profile of amino acids to the small intestines. So we're not wasting the protein that we had before. Getting something there that's much closer to where we are. So when I first started with rations and stuff, 15 to 16 for our MUNs was fairly standard, milk, urea, nitrogen. Now we're down to 10 and 12 is what most nutritionists are balancing for, or at least monitoring to see if everything's where it's supposed to be. So this comes back to, we need to talk about the urea cycle. One of the advantages of the dairy cattle is their ability to recycle urea. For most simple stomached animals, fine gut fermenters, to a point, urea is a waste product. Once it's formed, it needs to be excreted, it needs to be removed from the body, or bad things happen. With the ruminant, there's an opportunity to turn that back into protein. So urea, we look at that molecule there. We said it's about 280% crude protein. We've got a nitrogen here and a nitrogen here. The ammonia group can be taken off and the microbes can create an amino acid using the ammonia group as a building block or part of that amino acid. So how does the urea cycle work? Amino acids are degraded or recycled. The amino acids are split into the ammonia group and the keto acid. The two ammonias are taken to form one urea. So if we're not using our amino acids the way we should to build things. We're going to split off there. This is going to go one way. This is going to go the other. It could be burned for energy. This could be burned for energy or used to recycle some other way. The ammonia is very toxic to the body. So the liver has developed a system where we can take those two ammonias and form one urea. Urea isn't great for the body, but it's a lot less toxic to the body than the ammonias. We're getting these ammonias can raise the pH of the blood. Urea is more or less neutral from a pH standpoint. Urea is released from the liver, spreads throughout the body. There are a number of different ways you can measure that urea in the body. There's BUNS, blood urea nitrogen, PUNS, plasma urea nitrogen, or MUNS, milk urea nitrogen. These are all very tightly correlated. If they go up in one pool, the blood, they are also going to go up in the milk. We know that urea is pretty much lipophilic. It's going to diffuse through the body freely. So the concentrations throughout the body remain more or less constant. Depending on when we have, the kidney is the one way to remove it. So if we're looking at urea goes to the kidney, it will be removed and excreted through the urine. If the urea goes to the salivary gland, it goes into the saliva. We've got 60 gallons of spit being formed in the mouth and swallowed by a cow each day. And it's going to go into the rumen. If urea goes into the rumen, it can cross the barrier, the lining of the rumen. It's going to go into the rumen and be very rapidly used by the microbes. So if it goes into the rumen, what does it become part of? Does anybody want to guess? What? They do something with it. So urea normally is what? Part of our A fraction. So it doesn't matter whether it comes from the feed or it comes from the blood or the liver. The cow, the microbes in the rumen will take it and reform protein. So if the liver, for whatever reason, breaks down an amino acid, that breakdown product may be recycled back into the rumen and regenerated into protein. If we're looking at the ruminants running around Africa during the dry season, they're making their living off of grass that hasn't seen water in a while. That's like 4% protein. They can actually gain weight because of this urea cycle. Instead of excreting that urea, most of it recycles back into the rumen, and they can generate enough protein to grow and thrive even in the dry season. So when it's in the rumen, it becomes part of the A fraction. So if we're looking at our urea cycle in the cow, we have a lot of things happening in the liver. We can have amino acids that are made into proteins, blood proteins, and they're excreted throughout the body. Excreted from the liver, move through the blood, maybe part of the blood proteins, maybe part of things that get exported to other places. They can also degrade those amino acids into urea. So after leaving the liver, where does the urea go? We've alluded to this already. It goes to the kidney, the rumen. We'll see it in the milk as well. And it will end up probably in the manure as well. Problem is we don't see much urea in the manure. Anything that goes into that large intestine is going to be broken apart pretty quickly to ammonia. So it's very hard. You got to be pretty quick if you want to measure urea being excreted from the back end of a cow or any other hindgut fermenter for that matter. So the focus here with our rumen is the ability to recreate protein from the basic building block of urea, or more accurately, the ammonia group. So the urea is going to go to the kidneys, it's going to go to the salivary gland, or it's going to go to the blood supply of the rumen and reticulum, and it will be absorbed across the rumen wall. If it goes to the kidney, it's going to be lost to the bladder, lost in the urine. If it's recycled into the rumen, the urea can be combined with a carbohydrate that'll make the other half of the amino acid, and the microbes can recreate that amino acid, or any amino acid for that matter. So they'll take that urea, the two ammonia groups, combine it with a carbon skeleton from a carbohydrate, so our NDF, our starch, and they're going to build amino acids which they will use to live on. So what do we know about the urea cycle? Why do we care? So we need enough urea in the body. We need enough urea in the rumen to feed the microbes. That seems to be 10 to 12, I think it's milligrams per deciliter. That's what Sarah, our nutritionist up at the dairy, is looking at. She wants to see 10 to 12 on those MUNs when they come back from DHI every month. If they drop down into single digits, she's got to up the degradable protein fraction, the A and B fractions, to get a little bit more. Below 10, we're starving the rumen. They are not getting the building blocks to produce the amino acids that they need. If we're up in that 16, 17 region, we're wasting a lot of protein. The animals using it as an energy source, and since protein is more expensive than our carbohydrates, why feed extra protein be used as energy? We could do energy for energy, be a little bit cheaper. As we get up into the low 20s, we get to the point where things are going to affect other things in the body. We think of 2022 usually starts to interfere with the opportunity for pregnancy. As we said, urea can go anywhere in the body. It can go into the uterus, and there it tends to be spermicidal, especially if it gets broken up into two ammonias. That's going to throw the pH of the uterus off. That's going to be spermicidal. It's going to reduce our conception rates. It's going to reduce our pregnancies per month. So we want to make sure we get a good balance, enough A and B fraction into the rumen to allow that creation of ruminal protein, the microbial protein that the cow can use, but we don't want to have so much protein in the wrong forms, the wrong fractions, that it's excessive and causes problems. There's also some issues with the urea cycle. If you're dealing with most of those, the paleo diet, the Atkins diet, There's a few others where you're consuming a lot of protein, not a lot of carbohydrates. The idea is that you're using the protein as energy. The protein is the first step of creating energy with the protein is you got to split that amino acid up. The ammonia goes one way. The keto acid goes through the various metabolic pathways and is burned for energy. The challenge of this is making urea is a very expensive molecule energetically to make. So if we force the increase in urea production, what does that do to your maintenance costs at any given day? It's going to go up. To keep things running, to keep things going, if I've got to make more urea compared to another situation, that's going to increase my energy costs. So if I increase my maintenance cost, especially as I get older and stop growing, at least vertically, not horizontally, that is an opportunity to increase my maintenance cost. Therefore, I may lose weight faster. So any questions on that? Everybody see how that works together. So we got a couple minutes. Let's stay on this for a moment. So how do I get from the C fraction to the A fraction inside of cow? Comes in the mouth. That's part of the C protein fraction. How do I get to the A fraction? So C fraction goes where? Small intestines. Then what happens? Goes to the liver, gets broken apart. If it's broken apart at the liver, we can have urea formation. Urea circles around and becomes part of the A fraction in the rumen. So there's a bunch of intermediate steps in between. But that's how we get from the C fraction to the A fraction. We could do the same thing with the B fraction. B fraction becomes part of the microbe. The microbes go to the small intestine. Small intestine gets amino acids get absorbed to the liver. The amino acids get broken apart. They're going to swing back to the A fraction as that urea is manufactured in the liver, spreads throughout the body. If it goes to the gut first, it can be recycled into microbes over and over again, and you can keep that cycle going in theory forever. Any questions? So review session down the hall, 125B at 2 o'clock. And then we got a 5 be here after my class 200 this afternoon. That's all I have for today. If anybody needs student success seminar things, if anybody needs other ration sheets, we got them here. Anybody needs to sign up for advising, we have that sheet up front here. I think I know everybody now. I just checked them off. It's important that you're recorded here. I've got you recorded. If you want to double check.
Where are you meeting?
Yeah.
Saturday.
I don't know where the one The 11 o'clock-ish meeting will be. The 1 o'clock-ish meeting will be, hopefully I'll have some answers for you by Wednesday or
Okay.
Thursday. The 1 o'clock meeting will be up at the dairy.
Okay, there you go. Okay,
So I don't know. I think the last time we met in Spader were the 11 o'clock. So,
okay.
but I don't know for sure. So
Now,
we'll
can you
get
go
that.
to either the 1 o'clock or the 11, or do you want us to go to both?
You can go either or.
Okay.
So we don't, an hour of your time is more than enough.
I
So,
wrote my question
Thank
down
you.
before, but
Appreciate
you
it.
haven't answered my question.
okay, there you go.
Does this look out or no?
Yeah, it will.
All
So,
right.
Bill. Be
Okay.
here for the test, but I'm not here for lab.
okay, okay. So we gotta do some catching up. How do you want to handle that? You want to get to me next week? What do you want to do? What do you want to try to do before? What do you want to do?
When do you have time?
Probably Wednesday afternoon.
I'll be leaving at like 3 to go down to Harrisburg.
Okay,
So I guess I can do it afterwards.
okay. When will you be back?
Well, Friday night.
Okay,
I'll be back all next week.
okay. So we can check in on Monday, office hours, student hours, or whatever they're called. Or if you really want to, we could probably do something Sunday night. If it felt like it. Fall to Monday. If you change your mind, let me know Wednesday. Okay?